Picture this. You are a chemist in 9th century China, and you are not trying to build a weapon. You are trying to cheat death itself. You believe that somewhere in the right mixture of minerals, there is a recipe for eternal life, an elixir that will let an emperor rule forever. So you grind, you heat, you mix salt, sulfur, and charred wood, following instructions passed down through generations of monks who were just as obsessed with immortality as you are. And then, on one unremarkable afternoon, in one unremarkable workshop, that mixture does something nobody asked it to do. It explodes. No elixir. No eternal life. Just smoke, singed eyebrows, and a hole where a workbench used to be. The alchemists, searching for a way to live forever, had just stumbled onto the single most efficient way ever devised to end a life. They didn't know it yet, but they had just detonated the first shot in a chain reaction that would take 1,300 years to finish going off. A chain reaction that would tear down castles, end the age of the armored knight, and eventually put a weapon capable of killing at a distance into the hands of nearly every army on Earth. This is not a story that starts with a general or a king deciding the world needed a better way to kill. It starts with a mistake, a failed medicine, an accident nobody in that room wanted. And from that one accident, over the next 1,000 years, human beings would take fire itself and slowly, deliberately, teach it how to aim. This is the story of how we invented the gun. Before we go back to that workshop and follow this invention all the way to the modern battlefield, I want to ask you for something small. If stories like this, the ones where a single accident once quietly rewrites the entire course of human history, are the kind of thing you come here for, hit subscribe and tap the notification bell. We are trying to reach Sky's goal by the end of this month, and every one of you watching right now is part of how we get there. Already subscribed? Then you already know what's coming. Let's go back to the beginning. To understand how something built for eternal life became the ancestor of every firearm on the planet, you first have to understand what these alchemists were actually doing. Taoist alchemy in 9th century China wasn't fringe superstition practiced by a handful of eccentrics in the mountains. It was serious, state-sanctioned science by the standards of the time, pursued by scholars with imperial backing, because the person who discovered how to grant an emperor immortality would have secured a place in history, unlike almost anyone else alive. The formula that eventually mattered most combined 3 ordinary substances. Potassium nitrate, better known as saltpeter, mixed with sulfur and charcoal. Individually, none of these ingredients look particularly dangerous. Saltpeter occurs naturally in soil and old manure piles. Sulfur is a yellow mineral you can find near volcanic vents. Charcoal is just burned wood, but combine them in the right ratio and something remarkable happens chemically. Saltpeter is what's known as an oxidizer. It releases oxygen extremely fast when heated, feeding a combustion reaction so quickly that the burning gunpowder can't escape as smoke the way an ordinary fire would. Instead, it expands violently, all at once, as a hot expanding gas. That single physical fact, a huge volume of gas appearing in an instant, is the entire secret behind everything gunpowder would ever be used for. From a firework bursting over a festival crowd to a bullet, leaving a rifle barrel at supersonic speed centuries later. The earliest written references to this fire drug, or huoyao, describe it almost exactly the way you'd expect an accidental discovery to be described, with warnings. Alchemical texts from the era caution against combining these particular substances, noting that workshops had burned and that experimenters had been injured, sometimes badly, by mixtures that ignited unexpectedly during preparation. That's not the language of a weapons lab. That's the language of scientists who kept getting hurt by their own equipment. And were trying to warn the next generation, for a surprisingly long stretch of time after its discovery, gunpowder had almost nothing to do with warfare at all. Its first real applications were closer to entertainment than to combat. Fireworks lit up festivals and religious ceremonies across Chinese cities, and the same explosive mixture that would eventually flatten castle walls spent its early career mostly delighting crowds with noise and color. Fire arrows, essentially gunpowder-propelled projectiles, also appeared early, blurring the line between weapon and spectacle. Since a burning arrow trailing sparks across a night sky could be either a battlefield signal or a celebration, depending entirely on the context. It was Song Dynasty military engineers, watching the raw destructive potential of this substance, who first asked a very different question. What happens if we point this at an enemy? The answer, developed somewhere between the 10th and 12th centuries, was a weapon called the hua qiang, or fire lance, and it's genuinely difficult to overstate how crude and how effective this device managed to be at the same time. The design could not have been simpler. Take a length of bamboo, pack it with gunpowder, attach it firmly to the end of a spear, and light it in the middle of close combat. What came out the other end was a jet of flame, smoke, and burning debris aimed directly at whoever happened to be standing in front of you. It wasn't accurate. It wasn't reusable in the way a modern weapon is. But it turned an ordinary spear into something that could genuinely terrify an opponent who had never seen anything like it before. Historical records describe fire lances being used by defenders during the siege of a fortified city in 1132, where soldiers on the walls used the weapon against attackers attempting to climb up and breach the defenses. And by every surviving account, it worked exactly as intended, not necessarily because it killed large numbers of people, but because it introduced a kind of psychological shock that traditional weapons simply couldn't replicate. Soldiers trained their entire lives to fight sword against sword, spear against spear. None of that training prepared anyone to face a weapon that spat fire on command. That psychological effect mattered as much as the physical damage, and it's a pattern you'll see repeat again and again throughout this story. Every major leap in firearms technology carried a shock value beyond its actual battlefield statistics, at least at first. Innovation accelerated quickly once fire lances proved their worth. Someone, history doesn't record exactly who, had the idea of packing pottery shards and metal pellets into the bamboo tube alongside the gunpowder. Now the weapon wasn't just spitting flame. It was flinging small projectiles outward with real force. That single change represents the actual conceptual birth of the firearm as we understand it today. A tube, a propellant, and a projectile launched by expanding gas. Everything that followed for the next 1,000 years was, in one form or another, a refinement of that exact same basic idea. Bamboo, however, had a hard physical limit. As Chinese engineers packed more gunpowder into these tubes to make them more powerful, the bamboo simply couldn't handle the pressure. Tubes split, burst, pop, and occasionally injured the very soldiers holding them, which is exactly the kind of problem that forces innovation forward. The solution arrived once craftsmen learned to cast metal tubes strong enough to safely contain that same explosive pressure. This gave rise to the hand cannon, and one particular surviving example, a bronze weapon often referred to as the Heilongjiang hand cannon, is widely regarded as one of the oldest confirmed metal firearms in existence, dating to somewhere in the 13th century. Unlike a bamboo fire lance, a bronze hand cannon could be loaded with a proper charge of gunpowder and a single solid projectile, launched with considerably more force and considerably more range. This was no longer a modified spear. This was a genuine firearm, in the most literal sense of the word. Chinese engineers didn't stop at handheld weapons either. They scaled the same underlying principle upward into large siege devices with suitably dramatic names. Weapons designed to deliver massive explosive impacts capable of cracking open fortified positions that had stood firm against every previous form of siege warfare. Walls that had protected cities for centuries suddenly had a new and unfamiliar enemy to contend with. And then came the moment that turned a regional Chinese innovation into a truly global one: the Mongol conquest. When Mongol armies swept into China during the 13th century, they encountered gunpowder weapons directly on the battlefield during sieges where Chinese defenders used exactly the fire lances, hand cannons, and explosive devices described above against the invading forces. Rather than simply being defeated by this unfamiliar technology, the Mongols did something far more consequential. They adopted it. Once Mongol rule was firmly established over China, gunpowder weaponry effectively became part of the Mongol military toolkit, and Mongol armies carried that knowledge with them as their campaigns pushed westward across the breadth of Asia. It's worth pausing here, because this is genuinely one of the more underappreciated technology transfers in human history. Mongol military campaigns functioned almost like an accidental delivery system for gunpowder knowledge, moving it across enormous distances at a speed no trade caravan or diplomatic exchange could have matched. Within just a few generations, a chemical mixture discovered by monks in a specific region of China had been carried across the entire Eurasian landmass, reaching Central Asia, the Islamic world, and eventually the edges of Europe itself. Gunpowder technology didn't travel down a single road either. Alongside the hand cannon's slow migration westward, an entirely separate branch of the same discovery, rockets and fire arrows, spread along overlapping routes into Korea and India. Evolving independently as a distinct category of gunpowder weapon that never fully vanished the way the fire lance eventually did. Centuries later, that same rocket branch would resurface in European warfare, and much later still in the earliest ancestors of both military rocketry and space exploration. One accidental discovery, two separate technological lineages, both still shaping the world today. Historians studying this period also point out something worth appreciating. Gunpowder wasn't traveling alone. Paper, printing, and the magnetic compass were making the same general journey westward during roughly the same centuries, part of a much larger current of knowledge moving from east to west long before anyone had a word like globalization to describe it. By the time gunpowder technology reached Europe in the late 13th century, it landed in a political and military world built almost entirely around the armored knight and the fortified stone castle. A world that gunpowder weapons would spend the next several centuries systematically dismantling. Nowhere was this more dramatically visible than at Constantinople in 1453. Massive siege cannons, built specifically for the task, battered walls that had successfully repelled invaders for over 1,000 years. Those walls had survived siege engines, battering rams, and armies for centuries. They did not survive sustained cannon fire. When Constantinople finally fell, it wasn't just the end of an empire. It was a very public demonstration that gunpowder artillery had made an entire category of medieval defense obsolete almost overnight. The transformation this triggered went far beyond any single siege. Mounted knights in heavy armor, the dominant military force across Europe for centuries, discovered they were no longer untouchable because enough gunpowder-driven force could punch straight through steel that had once seemed impenetrable, regardless of how much a soldier had spent preparing for war the traditional way. The entire social and economic order built around expensive, heavily trained cavalry began to wobble, because a comparatively cheap weapon in the hands of a far less expensively trained soldier could now neutralize an opponent who represented a lifetime of investment. Castle architecture itself had to evolve or disappear. Tall, thin medieval walls, designed to repel scaling attackers and arrows, became dangerously vulnerable to cannon fire almost overnight in historical terms. Military engineers responded with the Star Fort and the Bastion, lower, angled, thickly reinforced fortifications specifically designed to deflect and absorb artillery rather than simply standing tall and hoping for the best. The medieval castle, an architectural form that had dominated the European landscape for centuries, was gradually replaced by something that looked almost nothing like it, all because of a substance that had originated half a world away, in the hands of monks who were never trying to build a weapon at all. Cannons could knock down walls, but they couldn't solve the much smaller, much more personal problem facing an individual soldier trying to fire a handheld gun accurately in the middle of a battle. Stop. Early hand cannons and their immediate successors were smoothbore, meaning the inside of the barrel had no internal grooving to stabilize a projectile in flight. That made them wildly inaccurate at anything beyond very short range, and firing one required an almost absurd amount of coordination. One hand to steady the weapon, the other to press a burning ember or a length of smoldering cord directly against a small touch hole, all while trying to keep the weapon pointed at a moving target on a chaotic battlefield. The matchlock mechanism, developed in the late 15th century, solved this specific problem with an elegant piece of mechanical engineering. A slow burning cord was held in a curved clamp called a serpentine, mounted directly onto the weapon itself. Pulling the trigger lowered that already burning cord into a small pan of priming powder, igniting the main charge automatically. For the first time in history, a soldier could actually hold and aim a firearm with both hands right up until the instant it fired, rather than juggling a weapon and an open flame simultaneously. This might sound like a modest mechanical tweak, but it was genuinely transformative, because it was the first mechanical firing device ever applied to a small arm, and it turned the firearm from a clumsy novelty into something a trained soldier could actually aim with real intent. Matchlock arquebuses spread rapidly across Western Europe through the early 16th century, particularly through Spain, France, and the territories of the Holy Roman Empire, before spreading further still across the breadth of Eurasia. The Ottoman Empire incorporated matchlocks into its elite Janissary Corps, using them to devastating effect in major engagements of the early 16th century. In 1543, Portuguese traders introduced matchlock technology to Japan, where local gunsmiths refined the design so thoroughly that Japanese matchlocks came to be regarded as among the finest crafted firearms anywhere in the world at the time, admired even by European observers for their precision. China, having started this entire chain of innovation centuries earlier, eventually reabsorbed an improved version of its own original invention, developing matchlock weapons to defend its northern frontier. a strange and fitting historical loop for a technology that began as a failed immortality potion in that same general region. Matchlock muskets eventually grew heavy and powerful enough to require a forked rest just to support the barrel while aiming. Stop, but they could punch through plate armor at ranges that made traditional swords and pikes increasingly irrelevant on an open battlefield. Because reloading took considerable time and left a soldier briefly vulnerable, musketeers typically needed protection from close combat, usually provided by pikemen standing alongside them. This combination of pikes and shot came to dominate European battlefields from the 16th into the early 17th century, an elaborate and carefully choreographed tactical system that required extensive training to coordinate effectively. But the matchlock had one glaring, universally understood weakness. It needed an open flame at all times. That made it nearly useless in wet weather, gave away a soldier's position in the dark, and required constant maintenance of a burning cord, even when nothing was happening on the battlefield at all. The wheellock, developed in the early 16th century, offered a partial solution by using a spring-loaded wheel spinning rapidly against a piece of pyrite to generate sparks, eliminating the need for a constantly burning match. This made wheellocks especially attractive to cavalry, who needed a weapon they could carry loaded and ready, without tending an open flame from horseback. But wheellocks were expensive and mechanically complex to manufacture, which kept them from ever fully replacing the cheaper, simpler matchlock among ordinary infantry. The true breakthrough arrived with the flintlock, generally credited to a French gunsmith who developed the mechanism in its recognizable, modern form during the early 17th century. The flintlock used a spring-loaded hammer holding a piece of flint, which struck a steel surface to generate sparks directly into the priming pan. It was faster to operate than a matchlock, dramatically more reliable in poor weather, and required no open flame to maintain at all, which also meant soldiers no longer gave away their position in the dark simply by carrying a lit weapon. By the 1630s, the flintlock mechanism had spread rapidly across Europe, quickly becoming the dominant firearm design across essentially every major European military, a position it would hold for roughly 2 centuries, right through colonial expansion, the era of European empire building, and every major conflict that followed, including the American Revolution, where flintlock muskets carried both colonial militias and regular soldiers defined the entire war from start to finish. The flintlock's rise coincided with another crucial innovation, the socket bayonet, introduced in the late 17th century. Unlike earlier plug bayonets, which jammed directly into the muzzle and rendered the gun unable to fire while attached, the socket bayonet attached around the outside of the barrel via a metal ring. This seemingly small change meant a soldier could fix a bayonet to his musket and still fire it normally, combining ranged firepower and close combat capability in a single weapon for the first time. Armies no longer needed dedicated pikemen standing alongside their musketeers for protection, since every soldier could now function as both shooter and spearman, depending on what the moment required. This infantry revolution simplified training, simplified logistics, and reshaped how European armies organized themselves for generations. For nearly 2 centuries, firearms had solved the problem of ignition without truly solving the problem of accuracy. Smoothbore muskets, whether matchlock or flintlock, still sent their projectiles tumbling somewhat unpredictably through the air, which is part of why massed volley fire, entire lines of soldiers firing in unison, remained the dominant tactic for so long. No individual shot needed to be precise if enough soldiers were firing in the same general direction at once. Rifling changed that equation entirely. By cutting spiral grooves into the inside of a barrel, gunsmiths discovered they could impart spin to a projectile as it traveled down the tube, and that spin dramatically stabilized the bullet's flight, much the way a well-thrown football spirals through the air far more accurately than one thrown, without any rotation at all. A spinning projectile resists the small aerodynamic imperfections that would otherwise cause it to tumble and veer off course. Rifled barrels had existed in limited form for a long time before this, but they were slow and difficult to load, since the bullet had to be forced tightly down a grooved barrel. It took further advances in bullet design and manufacturing before rifling became practical for widespread military use, ultimately extending the effective range and accuracy of the individual soldier far beyond anything a smoothbore musket could achieve. Around the same period, another transformation was happening in how firearms were actually loaded and fired. The percussion cap, introduced in the early 19th century, replaced the flintlock's loose priming powder with a small metal cap containing a shock-sensitive chemical compound that ignited instantly when struck by a hammer. This eliminated flint, steel, and exposed priming powder entirely, making misfires far less common and reloading considerably faster and more reliable, especially in wet conditions where flintlocks had always struggled. It was against this backdrop of rifling and percussion ignition that Samuel Colt introduced an idea that would fundamentally change personal firearms: the revolving cylinder. Instead of a single-shot weapon that had to be fully reloaded after every trigger pull, Colt's revolver design housed multiple preloaded chambers in a rotating cylinder, allowing a shooter to fire several shots in rapid succession simply by cocking the hammer again between pulls of the trigger. It's often said, somewhat dramatically, that Colt's revolver made all men equal, because for the first time, a single individual, regardless of size or physical strength, could carry a weapon capable of firing multiple rounds without reloading, changing the calculus of personal combat in the American West and far beyond it. This period of the 19th century represents a genuine inflection point in the entire story. For roughly 1,000 years, from the fire lance to the flintlock, gunpowder weapons had improved gradually, incrementally, often taking decades or centuries between meaningful advances. But the 19th century compressed that same rate of change into a matter of years, driven by industrial manufacturing techniques that allowed for precision, interchangeable parts, and mass production at a scale no earlier gunsmith could have imagined. The next transformation solved a problem that had existed since the very first fire lance: loading. For centuries, loading a firearm meant separately measuring gunpowder, packing wadding, and inserting a projectile, an involved process even for a trained soldier. The metallic brass cartridge changed all of that by combining the bullet, the propellant charge, and the primer into a single self-contained unit. A soldier no longer needed to manage 3 separate components under pressure in the middle of combat. Loading became a matter of inserting a single cartridge, and that single innovation opened the door to weapons that could fire far more rapidly than anything that came before. That door was fully kicked open by Hiram Maxim, an American-born inventor working in Britain, who introduced the first fully automatic machine gun in the 1880s. Maxim's design used the energy generated by each shot's recoil to automatically eject the spent cartridge, load the next one, and fire again, entirely without the shooter needing to manually cycle the weapon between shots. A single Maxim gun could fire hundreds of rounds per minute, sustained for as long as ammunition and cooling water held out. It represented the complete and total endpoint of everything this story had been building toward since a group of monks accidentally combined saltpeter, sulfur, and charcoal 1,000 years earlier. A weapon capable of turning gunpowder's expanding gas into continuous, mechanized, industrial-scale firepower. The consequences of that leap became horrifyingly clear within a few decades, when automatic and semi-automatic weapons, alongside modern artillery, transformed the nature of warfare itself during the early 20th century, rendering many of the tactics that had defined centuries of previous conflict catastrophically obsolete almost overnight. There's a strange and important paradox tucked into this entire history, one worth sitting with for a moment. The relentless pursuit of a better way to kill also drove some of the most significant advances in chemistry, metallurgy, and precision manufacturing in human history. Breakthroughs that quietly found their way into everyday civilian life. Techniques developed to manufacture interchangeable rifle parts helped lay the groundwork for modern mass production. Advances in metallurgy pushed forward by the demands of artillery and firearms eventually benefited engineering fields with nothing to do with weapons at all. Humanity's 1,000-year obsession with better ways to point fire at each other ended up, almost as a side effect, teaching us how to build almost everything else more precisely too. From a failed potion for immortality to a machine capable of firing hundreds of rounds a minute, the history of the gun is really the history of human ingenuity and our darker instincts arriving at the same destination together. Nobody set out on day one to invent the firearm. A group of monks looking for eternal life stumbled onto an explosive reaction and very nearly burned their own workshop down in the process. What followed wasn't a single flash of genius. It was 1,000 years of engineers, soldiers, and craftsmen watching that same basic reaction fail in some small way and quietly fixing it. Bamboo became bronze. Open flame became a spring-loaded mechanism. A single shot became 100 shots a minute. Each fix solved one specific, practical problem, and each fix passed through different hands along the way. Chinese engineers, Mongol conquerors, Ottoman soldiers, Japanese gunsmiths, and European craftsmen, each adding something of their own. We've mastered the fire within. The only question history keeps asking, over and over again, is where we choose to point it next. If this journey through 1,000 years of accidental invention was worth your time, our video on previous video link picks up exactly where a piece of this story leaves off. Go check it out, and I'll see you in the next one.